The variable vote is our outcome variable. It records the state-level vote share of the Democratic Party in a state election for a Senate seat in a given year. For example, the Democratic Party obtained 64.6% of the votes in the Senate elections of 1958 for one of the two seats representing State 1. This means that the Democrats won the 1958 election in State 1. The running variable is called margin. It records the margin of victory of the Democratic Party in the previous election for this Senate seat. The previous elections for this seat took place 6 years before in 1952. In that year, the Democratic Party also won the election with 57.5% of the votes, and the Republican Party lost with 42.5% of the votes. The difference, the margin, between the two outcomes is 15 percentage points. 15% is the value of the margin variable for the previous elections in 1958. Basic summary statistics of the outcome and the running variable show that there are missing values for the vote. This is because the election outcomes of 2006, 2008, and 2010 are missing in the dataset. There are a total of 1,297 complete observations. The vote values range from 0 to 100%. The variable margin ranges from -100 to 100. When the margin is above the 0 cutoff point, the Democratic Party is the incumbent for that seat. The unit is treated. Before carrying out any statistical analysis, I will test whether there is any evidence of manipulation of the running variable. For RD estimates to be valid, units should not have precise control of the running variable margin. Their characteristics, both observable and unobservable, should not jump at the cutoff, leading to comparable control and treatment groups. A lack of systematic selection around the cutoff is compatible with a continuous density of the running variable near the cutoff. The most straightforward thing to do is to present a histogram of the running variable margin using a large number of bins. I will choose 100. The bin widths should be as small as possible without compromising the ability to visualize the overall shape of the distribution. I want a reference line at the cutoff. I will add a plot to the histogram using the option PCI. The Cartesian coordinates of my reference line are 0, 0 to, let's say, 0.020. I do not see any clear bunching of units right around the cutoff. The relatively smooth distribution suggests that units have imprecise manipulation power over the running variable. Formal procedures exist to test if there is manipulation of the running variable at the cutoff, but you will have to program them or to download some Stata user-written command. One available command is RD density, followed by the name of the running variable margin. This command performs an automatic manipulation test based on density discontinuity. In the absence of manipulation, the density of the running variable should be continuous near the cutoff. This is a formal test of the null hypothesis that there is no discontinuity. The output suggests that at the cutoff 0, there is no evidence of manipulation. The null hypothesis is not rejected. The p-value is 0.38. Non-rejection suggests that there is no self-selection or sorting of units into the treatment around the cutoff. In principle, you should also check whether you have a sharp or fuzzy discontinuity. If units fully respect their assignment to the treatment, you have a sharp discontinuity, and a fuzzy discontinuity otherwise. In this example, I should test whether the Senate seats were, in practice, allocated to the winning party. Unfortunately, there are no variables in this dataset to implement that test. Now I will show you the results from some user-written RD estimation commands. The first step is to install those commands in your computer. Type ssc install rd in the command window. Then download the package of RD-related commands by typing findit rd robust. Click on the first link and then on click here to install. For a proper installation of these commands, you need Stata version 14. Let's start with the command rdplot, which creates an automatic graph of the RD design. The arguments are the dependent variable vote and the running variable margin. The rdplot command divides the running variable into a number of bins. There are 2 separate bins on each side of the cutoff to avoid having treated and untreated units mixed together in the same bin. The average value of the outcome variable is computed for each bin and plotted against the midpoints of the bins. By default, rdplot uses evenly spaced bins that mimic the underlying variability of the data. The visual impact of the graph is enhanced by 2 fourth-degree polynomials, one on each side of the cutoff. This relatively flexible model is a simple way of smoothing the graph. The fitted lines illustrate the natural shape of the underlying mean outcome functions and the size of the jump at the cutoff. In the Results window, you have information about the number of observations on each side of the cutoff, the order of the fitted polynomials, the number of bins on each side, and the lengths of those bins. It is a standard approach to plot the data this way before running regressions to estimate the treatment effect. Comparing the mean outcomes to the left and right of the cutoff point provides an indication of the magnitude of the treatment effect at this point. This graph shows evidence of a discontinuity at the cutoff point. There is no visual evidence of a discontinuity in the simple graph. It is unlikely the formal regression discontinuity will yield a significant treatment effect. Of course, these bins are too narrow to correctly estimate the treatment effect. The estimates will be highly imprecise. If we increase the length of the bins, the estimates may be biased as they are just averages and fail to account for the slope in the mean outcome function. More importantly, wide bins make the comparison on both sides of the cutoff less credible, as we are no longer comparing Senate seats with a small margin of victory. This takes us back to the question of how to choose the bandwidth around the cutoff. The bandwidth should be wide enough to include a sufficient number of observations and attain precise estimates, but the bandwidth should also be narrow enough to compare similar units and reduce selection bias. There are several techniques for choosing the bandwidth. The command rdbwselect implements a variety of bandwidth selection procedures for local polynomial regression discontinuity estimators. After the command, write the name of the outcome variable vote, the running variable margin, and the option bwselect to specify the bandwidth selection procedure to be used. The first method is called CV, cross-validation. For a linear polynomial approximation, in which p equals 1, the cross-validation method suggests a bandwidth of 35.4. Let me create a local macro, half of the bandwidth. I will add to the command rdplot a graph option indicating 2 reference points. To the left and to the right of the cutoff. The CV optimal bandwidth selector suggests I use observations within these 2 red lines and discard the rest. The second bandwidth selection procedure, proposed by Imbens and Kalyanaraman in 2012, is called the IK procedure. This option runs a data-driven algorithm to find an optimal bandwidth, which turns out to be much smaller than the previous choice. This is less than half of the cross-validation bandwidth. The third and last bandwidth selector was proposed by Kalanico, Cataneo and Titiunic in 2014. It is called CCT and it is the default algorithm. CCT has strong theoretical foundations, and unlike the last 2 procedures, CCT can be used in the context of fuzzy regression discontinuity or sharp regression discontinuity, as in this example. I will save the result of the CCT bandwidth under a local macro named BW. Finally, an RD treatment estimate can be computed using the command RD. The arguments are again the dependent variable vote and the running variable margin. The option BW allows me to use the CCT optimal bandwidth. The command RD fits local linear regressions, also called kernel regressions, on both sides of the cutoff. By default, this command weights the observations inside the bandwidth using a triangle kernel. RD estimates are sensitive to the choice of bandwidth. This command shows 3 different estimates calculated using 3 different window sizes: the requested bandwidth, half the bandwidth, 50%, and twice the bandwidth, 200%. In practice, applied papers present RD estimates with varying window widths to illustrate the robustness or sensitivity of the results to different specifications. The RD treatment effect is 9.64. This point estimate has optimal statistical properties. The interpretation is that when a political party barely wins the Senate election, when the margin of victory is around 0, in the following election for that same seat, the incumbent party gets a boost of 9.64 percentage points. There is another command that also estimates RD treatment effects. This command is RD robust. The arguments are the same, vote and margin. The default bandwidth comes from the CCT selector. The point estimate in the lower panel is 7.42. The output includes 2 confidence intervals. The second one is called the robust confidence interval, and it accounts for the fact that RD uses polynomials to approximate the underlying mean outcome functions. In this second confidence interval, the variance is corrected for the misspecification error or smoothing bias. The authors of this command suggest that the robust confidence interval should have good statistical properties, especially in relatively small samples, and should be used for statistical inference, for testing the statistical significance of a program impact. When implementing RD, it is advisable to implement some sensitivity tests. The general objective is to illustrate to what extent your results are sensitive to alternative specifications. It is essential to explore how your RD estimates are robust or not to different bandwidths, as well as to the use of higher order polynomial terms. You can add the option P2 to estimate the RD treatment effect with a second order local polynomial. Not only the treatment effect is still statistically significant, but the point estimate is quite similar. This is a good result. If the treatment effect vanishes when you use a higher order polynomial, your result is too sensitive and not very credible. Another type of robustness check consists of testing if jumps of the outcome variable occur at other placebo cutoffs or artificial cutoffs. There should be a treatment effect at the program participation cutoff, but there should be no similar jumps at other levels of the running variable without a reason. This test can help detect potential discontinuities over the support of the running variable. I can add the option C to test the treatment effect at the placebo thresholds of -50 and 50. Finding other treatment effects at other placebo thresholds suggests that the outcome variable is not properly modelled by your chosen polynomial, and you fail to capture or avoid its natural inflections. In this example, the treatment effect is not significant at the 10% level, at the 2 placebo cutoff points. Similarly, you can compute RD estimates on placebo outcomes. This falsification test builds on the idea that outcomes on which the treatment is known to have no effect should exhibit a zero RD treatment effect. I will compute the RD estimate of the effect of the margin of victory on the share of votes obtained in the last election for a different Senate seat. We should observe zero RD treatment effect at the cutoff. I will generate a placebo outcome that is equal to the vote variable in the previous observation, _n minus 1. _n is a built-in system variable that contains the number of the current observation. _n minus 1 is the previous observation. I use the prefix by sort to repeat state by state the generate command. I then estimate the RD effect on this placebo outcome. No treatment effect is detected, suggesting that continuity is satisfied and other underlying factors evolve smoothly at the cutoff point.